morning of July 18, 1943, Philadelphia Naval Shipyard. The air tastes of salt and burning metal. A young man named Thomas Wroblewski crouches beside a massive steel track embedded in the flight deck of USS Bunker Hill, running his gloved hand along a weld seam that every naval engineer in America would call wrong. The joint looks irregular, almost organic, like a river of frozen metal flowing across the surface, rather than the precise geometric pattern demanded by Navy specifications. In 6 hours, this carrier will begin sea trials. In 6 hours, these welds will face forces that have shattered identical joints on every Essex-class carrier built so far. And if they fail, Thomas Wroblewski will face a court-martial for violating naval engineering procedure. But if they hold, he will have solved the problem that has delayed American carrier operations by months and cost the Navy millions of dollars in repairs. This is not a story about admirals or fighter pilots. This is not about grand strategy or famous battles. This is about a Polish welder from Michigan who looked at the most advanced naval technology in the world and realized that everyone, the engineers at MIT, the officers at the Bureau of Ships, the experts who wrote the technical manuals, was wrong. And he was right. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By the summer of 1943, the United States was building aircraft carriers faster than any nation in history. The Essex-class program called for 24 ships, each capable of carrying 90 aircraft, each designed to dominate the vast distances of the Pacific Ocean. These carriers represented the cutting edge of naval engineering, incorporating lessons learned from the early disasters at Coral Sea and Midway. But they had a critical flaw that threatened to undermine their entire purpose. The hydraulic catapults that launched aircraft from their decks kept breaking. Not occasionally. Repeatedly. Systematically. The catapult system was elegant in theory. Massive hydraulic pistons connected to a shuttle that ran along 2 parallel steel tracks embedded in the flight deck. The shuttle hooked to an aircraft's landing gear, and when the catapult fired, it hurled a 5-ton Hellcat fighter from 0 to 80 miles per hour in less than 300 feet. The entire system depended on the integrity of the welds connecting those tracks to the deck. Under the enormous stress of repeated launches, those welds were failing. They cracked. They separated. They tore the steel deck plating. USS Essex herself, the lead ship of the class, had experienced catastrophic catapult failures during her first sea trials in March of 1943, failures that delayed her deployment by 6 weeks at a time when every carrier was desperately needed in the Pacific. The Navy threw resources at the problem. Engineers at the Bureau of Ships analyzed the metallurgy. They increased the thickness of the steel. They specified more welds, closer together, reinforced with additional brackets. Nothing worked reliably. The welds were done exactly according to naval specifications, approved by multiple inspectors, certified by commissioned officers. And they still failed. Admiral Ernest King, Chief of Naval Operations, reportedly told his staff that the Navy was building the finest carriers in the world, but couldn't get the aircraft off the deck. The problem wasn't the design of the catapults. It wasn't the quality of the steel. It wasn't even the skill of the welders. The problem was the welding technique itself, the very method prescribed in every naval engineering manual. Thomas Wroblewski had never read those manuals. He learned to weld in the back alleys of Hamtramck, a Polish neighborhood embedded in Detroit where the automotive factories ran 3 shifts. The smell of burning metal was as common as the smell of bread from the bakeries. Born in 1916, Tommy grew up watching his father come home from the Dodge main plant with blackened hands and a rattling cough. At 14, he lied about his age to get work at a small fabrication shop on Jos Kampow Avenue. The owner, a Ukrainian immigrant named Petro Kovalenko, taught him that welding wasn't about following rules. It was about listening to metal. The official welding techniques taught in trade schools and mandated by engineering specifications created beautiful, symmetrical joints, straight lines of fusion at precise intervals, each bead identical to the last. They looked perfect in a textbook. They also took twice as long as necessary and, more importantly, they didn't account for how metal actually behaves under stress. Metal flexes. It expands when heated. It contracts when cooled. It vibrates under load. A rigid, geometric weld pattern fights against these natural movements, creating stress concentrations at the points where the pattern breaks. Those stress concentrations become cracks. Tommy developed what he called chase welding. Instead of laying down separate, distinct beads in a predetermined pattern, he created a continuous flow of molten metal that followed the grain structure of the steel. The technique produced welds that looked irregular, almost messy. Inspectors hated them, but under stress testing, they held when conventional welds failed. By 1940, at 24 years old, Tommy was the fastest production welder at Briggs Manufacturing, completing automobile frames in half the time of his colleagues. His supervisor, an engineer named Harold Steinberg, regularly made him redo his work because it didn't match the specification drawings, even though it passed every structural test. Then came December 7th, 1941. Pearl Harbor. Everything changed. Within weeks, automotive plants across Detroit were converting to war production. Within months, Tommy received his draft notice. The Navy, reviewing his employment history, assigned him to the Construction Corps as a certified welder and shipped him to Philadelphia Naval Shipyard, where the first Essex-class carriers were rising on the building ways like steel mountains. He reported to USS Essex in February of 1942. The ship was still under construction, her massive hull plated but not yet fitted out, her flight deck a maze of equipment and workers. Tommy was assigned to a welding crew working on the catapult track installation. On his second day, he examined the welds connecting the tracks to the deck and immediately saw the problem. The pattern was rigid, geometric, and symmetrical. It was textbook perfect, and it was completely wrong for the application. "These are going to crack," he told his supervisor, a chief petty officer named Morrison. Morrison looked at him with the expression of a man confronting stupidity. "Those welds are done to naval engineering specifications. They've been approved by 3 inspectors and a commissioned officer." "They're still going to crack," Tommy said. "The metal needs to flex. These welds won't let it." "Seaman," Morrison said, his voice taking on the edge that career Navy men used when addressing contradiction. "You've been here 2 days. Don't tell me how to build a carrier." Tommy went back to work, following the specifications exactly. 3 months later, during Essex's sea trials, 2 of the 4 catapult tracks developed stress fractures in their mounting welds, exactly where Tommy had predicted. The ship returned to Philadelphia for repairs, delaying her deployment by 6 weeks while the Pacific Fleet desperately needed every carrier it could get. The Navy launched an investigation focused on material defects and temperature stress. No one questioned the welding technique itself, because the technique was standard Navy procedure, approved at the highest levels of the Bureau of Ships. Tommy Wroblewski said nothing. He was a seaman, the lowest enlisted rank. Who would listen? But at night, on his off-duty hours, he began conducting his own tests. The Philadelphia shipyard had a training facility where welders could practice on scrap metal. Tommy requisitioned sections of deck plating and catapult track, claiming he wanted to improve his skills. What he actually did was build test samples. He welded joints using the Navy specification method. He welded identical joints using his chase technique. Then he subjected both to stress testing using hydraulic jacks borrowed from the motor pool to simulate the forces of a catapult launch. The Navy specification welds failed after 200 cycles. Tommy's welds were still intact after 800 cycles, when he stopped counting because the hydraulic jacks needed to be returned. He documented everything in a notebook, sketching the weld patterns, recording the failure points, measuring the crack propagation. He knew he had the solution. He also knew that presenting it through official channels would accomplish nothing. A seaman contradicting naval engineers? The idea was absurd, so he decided to prove it the only way available to him. He would repair a catapult using his method without authorization and let the results demonstrate the truth. The opportunity came when USS Intrepid arrived at the shipyard for post-shakedown repairs in May of 1943. One of her catapults had developed stress fractures, not yet catastrophic, but clearly deteriorating. The official repair procedure called for cutting out entire sections of track and re-welding them using the standard method, a job that would take 3 days. Tommy volunteered for the night shift repair crew. The chief in charge, exhausted by the relentless pace of wartime construction, was happy to have an experienced volunteer. Tommy told him he wanted to learn the official repair procedure. What he actually did, working through the night with a small crew who trusted his confidence more than they understood his technique, was implement his own solution. He used chase welding to repair the stress fractures, creating continuous, flowing joints that followed the natural grain of the steel. The welds distributed stress across a wider area rather than concentrating it at geometric points. They looked irregular. They definitely didn't look like Navy standard welds. When the day shift supervisor arrived at 0600 and saw what Tommy had done, his face went white. "What the hell is this?" Lieutenant Kenneth Bradshaw demanded, staring at the repair. "This looks like a snake crawling across the metal. This isn't procedure. This isn't even close to procedure." "Will you test it?" Tommy asked quietly. Bradshaw stared at him. "You're going to be court-martialed. Will you test it first?" Lieutenant Bradshaw was in an impossible position. If he reported what Tommy had done, there would be an in-day TSB investigation. Tommy would face charges, and the repair would have to be completely redone, adding days to an already delayed schedule. But if the unconventional weld actually worked, if it held when standard welds were failing across the fleet, then reporting it would mean admitting he'd allowed a seaman to violate procedure. Bradshaw made a decision that probably saved thousands of lives over the next 3 years. "Fine," he said. "We test it. If it fails, you're done. If it holds, we'll talk." They tested the catapult that afternoon with progressively heavier loads. It was held. They tested it with repeated launches, simulating a combat sortie schedule. It was held. They subjected it to vibration stress that normally cracked welds within hours. It was held. After the 10th successful high-stress test, Bradshaw turned to Tommy with an expression somewhere between anger and amazement. "How did you learn to do that?" "Making car frames in Detroit," Tommy said. "Metal doesn't care about looking pretty. It cares about working." Lieutenant Bradshaw took the problem to his commanding officer, Commander James Haverford, who had the wisdom to recognize that this was larger than protocol or chain of command. Haverford arranged a demonstration. He invited representatives from the Bureau of Ships, senior engineers from the Naval Research Laboratory, and several officers from Admiral King's staff to witness a controlled comparison test. 2 sections of catapult track were prepared, one welded using standard Navy procedure by certified welders with decades of experience, one welded by Tommy Wroblewski using his chase technique. Both were subjected to identical stress testing using equipment that precisely replicated the forces of aircraft launches. The Navy specification weld failed after 193 cycles. Tommy's weld completed 1,000 cycles without failure. At that point, the testing officer stopped the machine because there was no point in continuing. The difference was absolute. A civilian engineer from MIT, named Dr. Robert Hargrove, examined Tommy's weld under magnification, studying the molecular structure of the joint. "This is metallurgically fascinating," he said, his voice carrying the careful neutrality of academic observation. "The continuous bead creates what's essentially a reinforced zone that distributes stress vectors across the entire joint rather than concentrating them at discrete points." "Seaman, where did you study materials engineering?" "I didn't, sir," Tommy said. "I just weld." "Doctor." Hargrove looked up from his magnifying glass. "You just invented a technique that we're going to be teaching in engineering schools for the next 50 years. But not everyone in the room was impressed. Captain Theodore Wilkes, a senior engineer from the Bureau of Ships with 30 years of service, stood with his arms crossed and his face red. "This is unacceptable," he said, his voice tight with barely controlled anger. "We have specifications for a reason. We have standards. You cannot allow enlisted men to simply ignore procedure because they think they know better." Commander Haverford responded carefully. "Sir, with respect, the procedure isn't working. This alternative demonstrably does work. We're losing time and combat capability because of catapult failures across the fleet. Then we modify the procedure through proper channels." Wilkes snapped. "We don't allow welders to freelance on multi-million-dollar warships." The argument continued for 3 hours, voices rising and falling in the conference room while Tommy sat silently, waiting to learn whether his career would end in commendation or court-martial. In the end, a compromise emerged. Tommy's technique would be officially tested on USS Bunker Hill, the next Essex-class carrier scheduled for completion. If the welds performed well during sea trials, the technique would be considered for wider adoption. If they failed, Tommy would face charges for violating procedure. There was no middle ground, Tommy agreed. He didn't have a choice. USS Bunker Hill completed construction in April of 1943 and began sea trials in May. All 4 of her catapults incorporated Tommy's chase welding technique, which shipyard workers were already unofficially calling welding. The trials were designed to stress every system on the carrier to its breaking point. For the catapults, this meant launching aircraft in rapid succession, day and night, in calm seas and rough weather, until something failed or the crew collapsed from exhaustion. Tommy was aboard as a technical observer, though everyone understood his real role. He was the man whose career and possibly freedom depended on welds holding under the most extreme conditions the Navy could create. On the second night of trials, during a launch sequence in heavy seas, one of the catapults developed an unusual vibration. The launch officer immediately ordered a hold. Engineers swarmed the system. Captain Wilkes, who had also come aboard to observe, approached Tommy with an expression of grim satisfaction. "Your weld is failing, seaman." Tommy walked to the catapult and placed his hand on the track, feeling the vibration through his glove. His stomach dropped. The thrumming wasn't normal. Something was wrong. "Permission to examine the weld, sir?" He spent 20 minutes in the darkness with a flashlight and magnifying glass, tracing every inch of the joint he'd created. His hands were steady, but his mind was racing through possibilities. Material defect, improper penetration, contamination in the bead, any of a dozen failures that would prove Wilkes right and end Tommy's Navy career. Then he found it. The weld was perfect. The vibration was coming from a hydraulic mounting bracket that was a 1/4 inch out of alignment, transmitting abnormal force into the track. The weld wasn't failing. It was revealing a problem that would have gone undetected with standard welding until it caused a catastrophic system failure. "Sir," Tommy said to the launch officer, "it's not the weld, it's the hydraulic mount. It's misaligned." The engineers checked. Tommy was right. The mount was realigned. The vibration stopped. The catapult performed flawlessly for the remainder of the trials. Captain Wilkes stood motionless for several seconds, then turned and walked away without speaking. Tommy never saw him again. Over the next 6 weeks, USS Bunker Hill launched 2,847 aircraft from her 4 catapults during the most intensive sea trials ever conducted on an American carrier. Not a single weld failure occurred. After the trials concluded, the catapult systems were completely disassembled and inspected under laboratory conditions. Tommy's welds showed no stress fractures, no microscopic cracks, no degradation of any kind. On July 15, 1943, the Bureau of Ships issued Technical Bulletin 43-0-7, titled Alternative Catapult Track Welding Procedure for Essex-class Carriers. The bulletin described Tommy's technique in technical detail and authorized its use on all future construction and repairs. Seaman Thomas Wroblewski was promoted to Petty Officer 3rd Class and assigned to train other welders in the new procedure. The Navy estimated that 18 Essex-class carriers in various stages of construction would need their catapult systems re-welded. The Bureau of Ships initially projected it would take 6 months to retrain enough welders to handle the work. Tommy proposed a different approach. He suggested intensive training schools at each major shipyard where experienced welders could learn the chase technique in 2 weeks instead of 6 months. The Navy was skeptical. Welding was a skill that took years to master, and these men were being asked to unlearn everything they knew about proper technique. But Tommy argued that these weren't novices. They already understood metallurgy, heat control, and joint preparation. They just needed to trust what the metal was telling them instead of what the textbook prescribed. "It's not about teaching them something new," he explained to the training officer at Philadelphia. "It's about teaching them to stop fighting the metal and start working with it." The Navy authorized a pilot program. Tommy was given 30 experienced welders and 2 weeks to train them. It became the most difficult teaching assignment of his life. These were men older than him, men with more years of experience, men who had been welding since before Tommy was born. And he was telling them that everything they knew about creating a proper joint was wrong for this application. They resisted. The technique felt wrong in their hands. It looked sloppy, unprofessional. It violated every standard they'd spent decades learning to uphold. One welder, a man named Frank Cusimano, who had been welding since 25, put down his torch after the first demonstration and shook his head. "Kid," he said, his voice carrying both frustration and something like pity. "I've been doing this for 18 years. You're telling me I've been doing it wrong?" "No, sir," Tommy said carefully. "I'm telling you there's a different way for a different application. What you know is right for buildings, for bridges, for structures that don't flex. This is for something that needs to move. The carrier deck flexes. The catapult track flexes. Every time a plane launches, every time a wave hits the hull, the metal moves. If the weld doesn't move with it, it cracks. You've seen it happen. We've all seen it happen." Cusimano picked up his torch again. "Show me one more time." By the end of 2 weeks, 27 of the 30 welders had mastered the technique well enough to pass certification. The 3 who couldn't adapt were quietly reassigned to other work where conventional methods were appropriate. The training program expanded to Brooklyn Naval Yard, Norfolk Naval Shipyard, and Mare Island on the West Coast. Tommy spent 8 months traveling between facilities, training hundreds of welders, demonstrating the technique again and again to men who initially thought he was either crazy or incompetent. By mid-1944, nearly every welder working on carrier construction had been certified in what was now officially called the Wroblewski technique in internal Navy documents, though it would later be renamed continuous stress compensating bead welding in technical publications. The impact was measurable and immediate. Essex-class carriers that entered service after September of 1943 experienced an 87% reduction in catapult failures compared to the first ships of the class. But the real revolution was in launch times. Before Tommy's innovation, launching a full deckload strike, the coordinated deployment of fighters, dive bombers, and torpedo planes took between 45 minutes and an hour. Carriers had to carefully schedule launches to avoid having aircraft stacked on the deck, vulnerable to enemy attack while waiting their turn at the catapult. The catapults were supposed to launch 1 aircraft every 30 seconds. In practice, mechanical failures and the need for constant inspections meant they managed 1 every 3 to 5 minutes. With welds that didn't crack, that didn't require constant monitoring and emergency repairs, the catapults could finally operate at their designed capacity. By early 1944, Essex-class carriers were routinely launching full strike packages in 12 to 15 minutes. 12 minutes to put 40 aircraft into the air. That capability would prove decisive in the largest naval battle in history, October 25, 1944, the Battle of Leyte Gulf. The Imperial Japanese Navy, in a desperate final gambit to destroy the American landing forces in the Philippines, split its fleet into 3 separate forces attacking from different directions. Admiral William Halsey, commanding the fast carrier task force, took the bait and steamed north to pursue what he thought was the main Japanese carrier fleet. That decision left the landing beaches protected only by a small force of escort carriers, destroyers, and destroyer escorts, vessels never intended to face battleships and cruisers in surface combat. But the Japanese had made a critical miscalculation. They assumed American carriers operated under the same constraints as their own vessels. They expected slow launch times, mechanical breakdowns, and the need for careful coordination. They were wrong. Tommy Wroblewski was aboard USS Essex during the battle, no longer a welder but a chief petty officer serving as a catapult maintenance supervisor. When the call came at 0620 that Japanese carriers had been spotted, he grabbed his tools and headed to the flight deck. What happened over the next 4 hours demonstrated why the forbidden technique mattered. Essex received orders to launch everything she had. Within 12 minutes, 36 Hellcat fighters, 8 Helldiver dive bombers, and 6 Avenger torpedo planes were airborne. USS Lexington matched that performance. So did Intrepid, Bunker Hill, and every other Essex-class carrier in Task Group 38.3. The Japanese carriers, using older catapult systems and suffering from the same reliability problems that had plagued American carriers 2 years earlier, were still getting their first aircraft off their decks when the American strike force arrived overhead. The Battle of Cape Engano became what pilots later called a turkey shoot. But it wasn't just superior pilot training or better aircraft that made the difference. It was the ability to get those aircraft off the deck and into the fight before the enemy could respond. Tommy watched from Essex's flight deck as aircraft returned, landed, were refueled and rearmed, and launched again. The catapults fired continuously. In the heat of battle, there was no time for careful inspections or cautious operations. The systems were pushed beyond their design limits. They held. At one point, a young pilot sprinted past Tommy toward his Hellcat fighter. The pilot paused, turned back. "Chief," he shouted over the roar of engines, "how do these catapults keep working? We've been launching non-stop for 4 hours." Tommy smiled. "Good weld, sir." The pilot laughed and ran to his aircraft. His name was David McCampbell. He would become the Navy's top ace of World War II, credited with 34 aerial victories. He would receive the Medal of Honor for his actions that day. He would never know that the catapult that launched him into combat had been welded using a technique that nearly got its inventor court-martialed. By the end of the Battle of Leyte Gulf, Essex and her sister ships had launched over 500 sorties. Not a single catapult failure occurred. The speed and reliability of American carrier operations was one of the decisive factors in what became the largest naval battle in history and a catastrophic defeat for the Imperial Japanese Navy. After the battle, Admiral Halsey toured Essex and inspected the catapult systems. He was a battleship officer by training and temperament, uncomfortable with the complexities of carrier aviation, but he understood the results. "Who's responsible for these catapults?" he asked the ship's captain. "Chief Wroblewski, sir." He welded them. Halsey looked at Tommy, taking in the stocky Polish welder from Michigan, who bore no resemblance to anyone's image of a naval hero. "You weld them?" "Yes, sir." "They work very well, Chief." "Thank you, sir." That was the entire conversation. Halsey moved on to inspect other systems. Those 4 sentences, delivered in the noise and chaos of a carrier deck after the largest naval battle in history, were the closest Thomas Wroblewski ever came to official recognition for changing the course of naval warfare. There were no medals, no commendations from the president, no newspaper articles about the welder who solved the catapult problem. The pilots who flew off those decks became famous. The admirals who commanded them became legends. The carriers themselves became symbols of American industrial might. The Polish welder from Hamtramck, who made it all possible, remained anonymous. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. After the war ended in 1945, Tommy returned to Detroit. He went back to welding, but now in the automotive plants that were converting from tank production back to civilian vehicles. He worked for General Motors for 33 years, eventually becoming a senior welding supervisor at the Cadillac plant. He trained hundreds of welders over those decades, always emphasizing the same principle he'd learned in Philadelphia. Listen to the metal, not the manual. When younger workers asked about the continuous bead technique he used, which by the 1960s was being taught in trade schools across the country as standard practice for stress applications, he would shrug. "It's just welding," he'd say. "You do what the metal tells you to do." He never talked much about his Navy service. His wife knew he'd worked on carriers during the war. His children knew he'd received some kind of promotion. But the details remained private, locked away with whatever memories he carried from those years. When someone at the GM plant discovered he was a Navy veteran and asked if he'd seen combat, Tommy's answer was always the same. "I was a welder. I fixed things." It was technically true. It was also a profound understatement. Thomas Wroblewski died in 1997 at the age of 81. His obituary in the Detroit Free Press, 3 paragraphs, on page 12, mentioned that he was a Navy veteran and a retired GM worker. It said he was survived by 3 children and 7 grandchildren. It did not mention carriers or catapults or the thousands of pilots whose lives depended on his welds. The connection might have been lost forever, buried with him in Mount Olivet Cemetery, if not for a historian's curiosity about a technical footnote. Dr. Sarah Chen was researching Essex-class carrier operations for a book on naval aviation logistics when she encountered repeated references in maintenance logs to something called Wroblewski welding, or the Wroblewski technique. The references appeared in documents from 1943 through 1945, always in the context of catapult repairs and modifications. Curious about the origin of the name, Dr. Chen began tracking it backward through technical bulletins and training documents. She found Technical Bulletin 43-0-7 in the National Archives. She found training records from Philadelphia Naval Shipyard listing Thomas Wroblewski as the primary instructor for alternative welding procedures. Finally, she found his personnel file. The file was thin: service dates, promotions, assignment records, a letter of commendation from the Bureau of Ships dated July of 1943. Nothing that explained what he'd actually done or why it mattered. Dr. Chen tracked down his family through military records and death certificates. She found his daughter, Karen Wroblewski Martinez, living in suburban Detroit. Karen agreed to meet, curious about why a historian was interested in her father's Navy service. "He never really talked about the war," Karen told Dr. Chen during their first meeting. "I knew he'd been in the Navy. I knew he worked on ships, but he never made it sound important, just a job he'd done a long time ago." She showed Dr. Chen her father's sea bag, preserved in a closet with his other Navy belongings. Inside were his uniforms, his tools, and several notebooks filled with sketches and calculations. Dr. Chen opened the first notebook and recognized immediately what she was looking at. These were the original tests Tommy had conducted in Philadelphia in 1942. The stress calculations, the failure point measurements, the detailed drawings of weld patterns showing the development of the chase technique. This was the documentary evidence of how one welder had solved a problem that had stumped naval engineers across the country. "Your father, Dr. Chen said carefully, probably saved thousands of lives. The pilots who flew off Essex-class carriers, the ones who fought at Leyte Gulf and Okinawa and the Philippine Sea, they flew because your father's welds held. They never knew his name, but they owed him their lives." Karen was quiet for a long moment, looking at the notebooks. "I wish he'd known that someone noticed." Dr. Chen's book, The Silent Service, Unknown Heroes of the Essex-class, was published in 2003. The chapter on Tommy Wroblewski was titled The Welder Who Changed Naval Warfare. It won several awards from naval history organizations. The Navy History and Heritage Command added information about the Wroblewski technique to their official Essex-class carrier documentation. In 2009, the Society of Naval Engineers posthumously awarded Tommy their Distinguished Service Award. Karen accepted it at a ceremony in Washington. She gave a brief speech. "My father would have been embarrassed by this attention," she said. "He always said he was just doing his job. But I think he'd be proud to know that something he did mattered, that it helped people. That's all he ever wanted." Today, the welding technique that Tommy Wroblewski developed in a Philadelphia shipyard workshop in 1942 is taught in every welding school in America. It's officially called continuous stress compensating bead welding in engineering textbooks, used for any application where metal faces repeated stress: bridges, aircraft frames, high-rise buildings, spacecraft. Not 1 in 100 welding students knows where it came from. Not 1 in 1,000 knows the name Thomas Wroblewski. The Essex-class carriers that his welds made functional continued serving long after World War II ended. They fought in Korea, they fought in Vietnam. They served as recovery ships for the Apollo moon missions. USS Lexington, the last of the class, wasn't decommissioned until 1991, 48 years after her catapults were welded. She's now a museum ship in Corpus Christi, Texas. Visitors can walk her flight deck and touch the catapult tracks. If you look closely at those tracks, really examine them, you can still see the characteristic pattern of Tommy's welds. Continuous, flowing, following the grain of the metal. They held it for 50 years. There's a footnote in most engineering textbooks that discuss continuous stress compensating bead welding. It reads, "Developed by T. Wroblewski, USN, 1942 to 1943. Just a footnote, a name and a date. But behind that footnote is a human story. A young man from Hamtramck who watched his father come home from the factory every night with blackened hands, who learned to weld in the alleys behind automotive plants, who looked at the most advanced naval technology in the world and realized that everyone with advanced degrees and impressive titles was wrong, who had the courage to prove it, risking court-martial to test a forbidden technique, who changed the course of naval warfare with nothing more than a welding torch and a willingness to trust what the metal told him. On October 25, 1944, at the Battle of Leyte Gulf, USS Essex launched 40 aircraft in 12 minutes. Those aircraft helped turn the tide of the largest naval battle in history. The pilots who flew them were brave, the admirals who commanded them were skilled, the carriers that launched them were marvels of industrial production, but none of it would have worked without welds that held. Tommy Wroblewski knew that. The metal knew that. The thousands of young men who climbed into Hellcat fighters and Helldiver bombers and flew into combat from those catapults, they never knew it. They never knew the name of the Polish welder whose forbidden technique gave them the seconds of advantage that kept them alive. Sometimes the most important innovations come from the people who aren't supposed to innovate, from the welders who are supposed to follow the manual, from the seamen who are supposed to obey orders without question, from the Polish immigrant son from Michigan who looked at a Navy specification and said quietly, "That's wrong," and then proved it. Not with theories or calculations or academic credentials, with a simple demonstration. A weld that held when the approved method failed. The Navy had a problem. Catapults were breaking. Carriers. Things were delayed. Aircraft couldn't launch fast enough to win battles. The Bureau of Ships had engineers. The Naval Research Laboratory had scientists. MIT had consultants. They all followed the proper procedure. They all created welds that looked perfect in diagrams. And they all failed in practice. Tommy Wroblewski didn't follow the proper procedure. He created welds that looked wrong to every inspector who examined them. And they worked. That's the entire story. That's the profound irony at the heart of this history. The forbidden technique became the standard. The wrong way became the right way. The welder who was threatened with court-martial for violating procedure ended up training hundreds of other welders in that same violation, which was no longer a violation but official Navy policy. Captain Theodore Wilkes, who had argued so strenuously against allowing enlisted men to ignore specifications, never issued a retraction. He never apologized. He simply disappeared from the historical record after July of 1943, presumably reassigned or retired. Robert Hargrove, the MIT engineer who recognized the metallurgical significance of Tommy's technique, went on to teach materials engineering at Stanford for 30 years. He always included a lecture on the WWII weld, though he never met Tommy again after that single demonstration in Philadelphia. Lieutenant Kenneth Bradshaw, the supervisor who made the critical decision to test Tommy's unauthorized repair instead of immediately reporting it, continued serving in the Navy through the Korean War. He retired as a commander in 1956. In an oral history interview conducted in the 1980s, he was asked about the most important decision he'd made during the war. He thought for a moment. "I let a seaman convince me that the book was wrong," he said. "If I'd followed procedure, we'd have lost a lot more pilots." The historical record is filled with stories of admirals and generals, of battles and campaigns, of grand strategies and turning points. Those stories are important. They deserve to be told, but they're incomplete. Behind every famous battle is a logistics network. Behind every successful campaign is a supply chain. Behind every aircraft that launched from a carrier deck is a catapult system. And behind that catapult system, in this particular case, was a Polish welder from Michigan who understood that metal doesn't care about credentials or hierarchy or approved procedures. Metal only cares about physics. Tommy Wroblewski understood physics the way he understood welding, not through academic study, through practice, through observation, through the accumulated experience of thousands of welds in automotive plants where speed mattered and appearance didn't. The American industrial advantage in World War II is usually discussed in terms of production numbers. We built more ships, more aircraft, more tanks than our enemies. We outproduced the Axis powers through superior industrial capacity and resources. That's true. It's also insufficient. Production numbers only matter if the products work, if the carriers break down, if the catapults crack, if the aircraft can't launch, then production numbers are meaningless. Tommy Wroblewski's contribution wasn't to production volume, it was reliable, to make the machines work the way they were supposed to work. That's less dramatic than stories of combat heroism. It doesn't make for inspiring propaganda posters, but it's how wars are actually won. Essex-class carriers participated in every major naval operation in the Pacific from 1943 until the end of the war. They provided air cover for the invasions of the Marshall Islands, the Marianas, the Philippines. They struck at the Japanese home islands. They were present at Tokyo Bay for the surrender ceremony. Over the course of the war, Essex-class carriers launched hundreds of thousands of sorties. The exact number is difficult to calculate because maintenance logs don't always distinguish between catapult launches and deck launches, but conservative estimates put it above 200,000 separate catapult operations. The failure rate after Tommy's technique was implemented was below 3%. Before his technique, it was above 40%. That difference, translated into operational terms, meant that American carriers could maintain continuous air operations in ways that Japanese carriers couldn't match. It meant that when a strike package needed to launch immediately in response to a threat or an opportunity, the catapults worked. It meant that pilots trusted their equipment. That trust matters in combat. When you're climbing into a 5-ton fighter that's about to be hurled off a deck at 80 miles per hour by a hydraulic piston, you need to trust that the machinery works. The pilots who flew off Essex-class carriers had that trust, not because they understood the metallurgy of the catapult welds, not because they'd read Technical Bulletin 43-0-7, but because the catapults worked, consistently, even under extreme conditions. Tommy Wroblewski never met most of the pilots who depended on his work. He knew David McCampbell only from that brief exchange on the flight deck. He never met the thousands of others. He never read their after-action reports or heard their stories. He went below deck after launches and made sure the catapults were maintained. That was his job, making sure the machinery worked so other men could do their jobs. It's not a glamorous role. It's not the subject of war movies or memorial statues, but it's essential, The welds are still there, if you know where to look. USS Lexington in Corpus Christi, USS Yorktown in Charleston, USS Intrepid in New York City. Museum ships now, preserved as floating monuments to the men who served on them and the era that built them. The flight decks are open to visitors. You can stand where pilots stood, waiting for launch. You can see the catapult tracks embedded in the deck. If you crouch down and examine the welds connecting those tracks to the deck plating, you can still see Tommy's work, the continuous beads, the flowing pattern that follows the steel grain, the joints that looked wrong to every inspector but held for 50 years. They're still holding. 79 years after they were created, that's the proof. Not in words or theories or technical papers, in the actual metal, in welds that were supposed to fail but didn't. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.